Welcome students. Today we'll be talking about the alpha decay process and Gamows theory. So alpha decay process is a process in which some unstable nuclei they try to give off their excess energy by emitting a doubly ionized helium nucleus, which is known as the alpha particle. So this is the phenomenon of radioactivity which we have discussed. So there are basically three kinds of decay: radioactive decay, the alpha decay, the beta decay, and the gamma decay process. So in the alpha decay process, a radioactive nucleus, it emits an alpha particle. So it emits an alpha particle that is a doubly ionized helium nucleus. So we have already discussed about what is this alpha particle and what are its basic properties. So it's a doubly ionized helium nucleus, as we have talked about. It's a positively charged particle which is affected by electric and magnetic fields. It can ionize matter as they pass through it, ionize gases as they pass through it. Also, it has penetration power. It can penetrate through material, through substances, through gases, etc. So, this alpha particle being emitted by an alpha particle source or a radioactive source, it has its own inherent energy with which it is emitted. So, we can talk about the energy of alpha particles, and this energy of alpha particles, it is different for different alpha emitters. So it depends on the disintegration constant of the alpha emitter, and it is inherent to the alpha emitter. So different emitters will emit alpha particles with different energies at different rates. So we can have a measure of the energy of alpha particles. Also, depending on its energy, the alpha particle can travel different distances as it passes through matter. So what happens when an alpha particle passes through matter? It collides with the atoms or molecules of matter, and this matter can be in the form of a gas. Usually we talk in terms of alpha particles passing through a gas. So it will cause ionization in the process by knocking off electrons from the orbits of atoms. So as a result, as an alpha particle passes through matter, its energy successively reduces. So till it reaches a point when the alpha particle can no longer cause ionization. So at that point, what will happen? The alpha particle will, absorb two stray electrons, and it will convert itself into a neutral helium atom. So basic idea is, when alpha particle travels through matter, after traveling a particular distance through matter, it ceases to exist. So this distance through which an alpha particle can travel through matter before ceasing to exist is called its range. Now, this range is dependent on the energy of the alpha particle. Higher the energy of the alpha particle, longer will be its ranges. So this is something which can be experimentally measured. The range of the alpha particle can be experimentally measured. So if we have different sources of alpha particles, we can measure the ranges of the alpha particles emitted by the source, which will indicate the energy of the alpha particles. So studies were done on the energy and hence the ranges of alpha particles emitted by sources. So there is a particular empirical law, which is an empirical law means from experimentally observed data. Geiger and Nuttall gave a law which relates the disintegration constant of the alpha emitter to its range. So simply means there is a linear relationship between the disintegration constant of the alpha emitter and the range of the alpha particles being emitted by the source. Here A and B are constants. This is a logarithmic relationship. So Geiger and Nuttall By measuring the ranges of alpha particles emitted by different sources having different disintegration constants, gave a law for this. This is known as the Geiger-Nuttall law. So if it is plotted, logarithm of the disintegration constant and the range, here it is x, rather we can put it as r, log of r, it's found to have a linear relationship. So these are the three naturally occurring radioactive series, radium, thorium and actinium. So these alpha particles being emitted by the source, because of the different emitters, they are found to have a linear relationship. Now, as we talked about, the range of the alpha particle is dependent on its energy. So the relationship is found to be range is proportional to e to the power 3 by 2. So the Geiger-Nuttall law can be written in terms of the energy as this, where C and D also are again constants which are characteristic of the alpha emitter. Now we have to talk about Gamows theory. The Geiger-Nuttall law, as we talked about, it's an empirical law from experiments. So Gamow gave a theory for the alpha decay process, and he tried to theoretically derive a relationship between the disintegration constant and the range and hence energy of the alpha particles being emitted by different sources. So that is Gamows' theory of alpha decay. So this is a theory. Geiger-Nuttall law is from experimental observations. So Gamows' theory is based on the following assumptions. So within the nucleus, the alpha particle may exist, which are in constant motion hitting the walls of the nucleus. So we do not exactly know what happens inside the nucleus. Alpha particle is 2 proton and 2 neutron which comes out together from the nucleus. So what Gamow said is that within the nucleus, the alpha particle may exist as a single entity and they are in constant motion inside the nucleus and they keep on hitting the walls of the nucleus. However, the surface barrier of the nucleus prevents it from coming out of the nucleus. At each strike, there is a finite probability of the alpha particle tunneling out of the nucleus. So this tunneling part is the quantum mechanical tunneling process that we are talking about. We'll discuss more about it. So this alpha particle process is a process which cannot be explained classically. So we have to use quantum mechanics to explain this process. So this process of quantum mechanical tunneling is used to explain the alpha particle coming out of the nucleus. So the quantum mechanical tunneling process can be illustrated as by the following figure. Suppose we have a barrier which we want to cross. So classically, you will need sufficient energy to go over the barrier and go to the other side. Suppose I need to push a stone over this barrier. So this is the classical picture. However, quantum mechanically, even if we don't have sufficient energy to cross the barrier, we can tunnel through the barrier. So this is a simple illustration of the quantum mechanical tunneling process. So even if the particle has energy lesser than the barrier height, it can tunnel through the barrier. There is finite probability that the particle will tunnel through the barrier. So instead of this stone, let us say that this is the alpha particle and this is the potential barrier of the nucleus, the surface barrier. So classically, the alpha particle should never be able to come over to the other side, means it should not be able to cross the barrier, surface barrier of the nucleus. However, experimentally it has been found that the alpha particles do come out of the nucleus even if the energy possessed by the alpha particle, experimentally measured energy possessed by the alpha particle, is less than the barrier height. So only way we can explain this is using the quantum mechanical tunneling process. So let us see what actually happens to the alpha particle. Inside the nucleus, the alpha particle is acted upon by an attractive nuclear force. So this we know because in the nuclear dimension, the force that is in operation is the strong nuclear force. So obviously, inside the nucleus, the alpha particle is acted upon by the attractive nuclear force. Outside, suppose somehow it comes out of the nucleus. Once the alpha particle comes out of the nucleus, the atomic number of the nucleus it reduces by 2. So the residual nucleus will have a charge Z-2e. The residual nucleus also is positively charged. The alpha particle is out of the nucleus. It has 2 units of positive charge. So once it is outside the nucleus, somehow it escapes from the nucleus. It is under the influence of the electrostatic repulsive force due to the residual nucleus. So this is the potential seen by the alpha particle. Inside, it's attractive negative potential. Outside, this is the Coulomb potential. Coulomb potential is which goes as 1 by R. So what happens? Suppose this is the surface of the nucleus. So this should actually go to infinity classically. This should be very high. So this is the surface barrier. So at the surface of the nucleus, there is a transition from an attractive to a repulsive force. So a negative potential to a positive potential. So this is the potential as seen by the alpha particle. So here we are showing it again. Suppose this is the dimension of the nucleus within this region D to C, and R is the range of the nucleus. So at the point R, there is a transition. This is the surface of the nucleus. There is a transition from an attractive force to a repulsive force. So the Coulomb force, it goes as 1 by R, 1 by R square. So just at the point when the alpha particle is out of the nucleus, R will tend to 0. So theoretically, the barrier height should go to infinity when R tends to 0. So this is the potential as seen by the alpha particle. And let us say the alpha particle has an energy E alpha. So this is the region BEA we are talking about. BEA, the Coulomb potential is goes as 1 by R. So it goes down like this. Now, the region RH, this region, is a region of negative kinetic energy. Why? Suppose the alpha particle has an energy E alpha. So this E alpha possessed by the alpha particle, let us say when it is inside the nucleus also it has E alpha. This E alpha is less than the barrier height. It is less than the barrier height. So classically the alpha particle should not be able to come out of the nucleus because E alpha is less than the barrier height. But we find experimentally that the alpha particles do come out of the nucleus. Now this E alpha is the total energy possessed by the alpha particle, that is equal to the kinetic energy plus the potential energy. And the potential energy is given by this value of the potential energy. Now in the region RH of the potential, you can see that the potential energy is greater than the total energy of the alpha particle, E alpha. Again I am telling you, in the region RH, the potential energy is greater than the total energy of the alpha particle. So the kinetic energy, which is equal to total energy minus the potential energy, will be negative in this region. But classically we know kinetic energy goes as V square. So if we have to have negative kinetic energy, it is not allowed classically. So RH is a region where the particle needs to have negative kinetic energy. If it is negative, then the the velocity becomes imaginary. So classically, no particle can exist in this region RH. Beyond the region RH, at the point H, E is equal to potential energy. So this is fine. The kinetic energy becomes equal to 0. So beyond this, no problem, because this is the region where it has finite positive kinetic energy. But this is the region which is of concern, because RH is a region where classically no particle can exist, because if any particle has to be there within this region, it has to have negative kinetic energy, hence negative imaginary velocity. So this is the region which can't be explained classically. So the alpha particle should not be able to cross the barrier because it has lesser energy than the potential barrier. However, experimentally it has been found that, suppose for example 222 radon, the alpha particles emitted by this has maximum 4.88 MeV of energy. However, the surface barrier of this nucleus of radon is 34 MeV. So classically we can never explain how the alpha particle having energy 4.88 MeV escaped from this nucleus having a surface barrier of 34 MeV. So only way we can explain this is using the theory of quantum mechanical tunneling. The alpha particle keeps on striking the wall of the nucleus repeatedly with a finite probability that it tunnels through this barrier. So this is the barrier. So this is quantum mechanical tunneling. So we have to consider quantum mechanical tunneling to explain the alpha decay process. So whatever we will be doing beyond this is talking about the quantum mechanical tunneling and developing a theory for that. So Gamow, he developed a theory which gave a probability of the alpha particle coming out of the nucleus. So he considered a rectangular shape potential of width A and one-dimensional height V. Instead of considering the actual potential, initially he said, let us consider a barrier height. So this is a problem which we do in quantum mechanics, the transmission probability. So Gamow first considered a rectangular shape potential of this form, three regions, region 1 inside the nucleus, region 2 inside the region of, suppose, RH. Instead of considering a potential of this form, he considered a step potential. So this is the region where the region of negative kinetic energy, let us say, and this is the region outside the nucleus. So he considered a step potential of this form, region 1, region 2 and region 3. So the wave function of region 1, he called it U1, region 2 U2 and region 3 U3. He wrote down the Schrodinger's equations for the three regions. U1, U2, U3 are the wave functions in the three regions. So for region 1 and 2, which has both the, let's go back to that again, region 1 and 2, they have the incident wave and the reflected wave. The alpha particle is the incident on the barrier, suppose. So part of that is reflected and part of it is transmitted through the barrier. So region 1 has incident and reflected. Region 2 also has incident, the other end of the barrier, and reflected. Region 3 has only the transmitted waves. So he wrote down the Schrodinger's equations for the three regions 1, 2 and 3. So region 1 and 2 can be written as this. So these are regions where we consider the potential to be 0. This is equation 1. And E is the energy of the alpha particle. M is the reduced mass of the alpha particle and the residual nucleus. For region 2, where this finite potential is there, we can write down the Schrodinger's equation as d2u dr square plus twice m by h cross square E minus v u is equal to 0. So region 1 has both incident and the reflected waves. The solution for equation 1 for region 1 can be written as this. This is from the theory of differential equations. writing down the solution of second order differential equation, where K1 is equal to root over twice me by h cross square. These are the wave vectors, where E is the energy of the alpha particle. So we can write down the solution for region 1 as this, and for region 2, which has both the incident and the reflected wave, the solution can be written as U2 is equal to A2 e to the power K2R, B2 is equal to e to the power minus K2R. Okay, here we are talking about this is the incident and this is the reflected. You can see the wave vector negative sign here is positive. So this represents the incident wave, and this the reflected wave from the barrier. A1 and B1 are constants here. Similarly, for region 2, we can write the solution to be A2 e to the power K2R incident and the reflected. For region 3, which is only the transmitted wave, the solution can be written as U3 is A3 e to the power IK1R. This is the transmitted. So here A1, A2, A3, B1 and B2 are constants which are to be determined from the boundary conditions of the problem. So what are the boundary conditions of the problem? The boundary conditions of the problem are U1 is equal to U2 and del U1 del R is equal to del U2 del R at R is equal to 0. U2 is equal to U3. These are the two boundary conditions, and del U2 del R is equal to del U3 del R at R is equal to A. These are from the properties of wave functions. So if you see here, these are the two regions, R is equal to 0 and R is equal to A. So U1 should be equal to U2 and first derivative of U1 should be equal to first derivative of U2. These were from the requirements of the continuity of the wave function, means the continuity of the probability of the particle in these two regions. These are basically the properties of the wave functions, and U2 should be equal to U3 at this boundary, and del U2 del R first derivative should be equal to first derivative of this. The continuity of the probability and the momentum of the particle gives rise to these two boundary conditions. So using these boundary conditions in the above solutions, we can get A1 plus B1. These are the result that we get by putting these boundary conditions in these solutions. So this is the first solution we are talking about, U1, then U2, U3. So using these boundary conditions, U1 should be equal to U2 and del U1 del R should be equal to del U2 del R at R is equal to 0, and the second boundary condition will end up with a relationship between the constants. So these are the four equations that we get using the boundary conditions. Now, playing around with these equations, we can find out expressions for A2 and B2. From these four equations, we can find out expressions for A2 and B2. So A2 is equal to this in terms of A3 and B2 is equal to this in terms of A3. Again, from equations 9 and 10, we get A1 in terms of A2 and B2. So we find out values of A2 in terms of A3, we find out B2 in terms of A3. Then we find out A1 in terms of A2 and B2. Our final aim is to find out a relationship between A1 and A3. Why? Because we want to find out, this is the region within the nucleus, constant for the alpha particles within the nucleus, and A3 is the constant for the alpha particle outside the nucleus. So we want to find out the transmittivity. So putting the values of A2 and B2 from this in this equation, we'll end up with a relationship between A1 and A3 in terms of A3. A1 is related to A3 by this equation. However, okay, as the velocity of the alpha particle in the regions 1 and 3 are same, Hence, the transmission probability of the alpha particle can be written as transmitted flux by incident flux. So transmitted, this is the amplitude of the, it's a constant, it represents the amplitude of the alpha particle outside the nucleus, A3, A1, inside the nucleus, into the velocity. So intensity into velocity, this is the transmitted flux and incident flux. So the transmittivity can be written as A3 by A1 whole square. First term in equation 15 can be neglected, since in practice K2A is greater, it's very large basically. K2 is root over twice m by h cross V minus of E. Now V is the barrier height, it's very large compared to E, that is the energy of the alpha particle. So basically K2A is a very large quantity. So in equation 15, this equation, first term, it goes as e to the power I k1a and e to the power minus k2a. So k2a is a very large quantity. So e to the power minus infinity, we know it is 0. So e to the power minus of a large quantity, so this will go very near to 0. So we can neglect this term in the equation. So we'll end up with a relationship between A1 and A3 where only the second term remains. So we neglect the first term. So therefore we can write A1 by A3. These are complex quantities. So it is A1 by A3 whole square is A1 by A3 into A1 by A3 conjugate. Right? So from that equation, we write A1 by A3 and the conjugate, we multiply it together, this equation. So this term we are putting it equal to 0. So conjugate A1 by A3 we get is equal to 1 by 4 into this e to the power I k1 plus k2a. So conjugate of this becomes 1 by 4, 1 plus I k1 by k2, 1 plus k2 by I k1. So e to the power minus k1 and plus k2a conjugate. Write the conjugate of a1 by a3. So what we get after doing that, a1 by a3 and its conjugate, we get this expression e to the power 2 k2a. So this we can simplify as 1 by 16, 1 plus k1 square by k2 as this e to the power k2a, 1 by 16, k1 square plus k2 square, k1 square, k2 square, whole square e to the power 2 k2a. So the transmittivity of the barrier is given finally by this expression e to the power minus 2k2a. Now if we put back the values of k1 and k2 in this expression, k1 is root over twice m e by h cross and k2 is root over twice m v minus e by h cross. So if we put it back here and considering that v is greater than e is usually of the order of 1, the maximum value being maximum value being 4. Okay, experimentally measured values of alpha particle energy from sources somewhere around 4. If we use that for the redden nucleus also, let us say V to be equal to around 32 and suppose E to be around 4. So it's found that the value of this is usually of the order of 1, the maximum value being 4, experimentally observed. So the final expression can be, transmittivity can be written almost equal to e to the power minus 2k2a. So physics, as we say, it's a subject of approximations. So these are approximations that we use in the Gamows theory. So this equation represents the fraction of alpha particles that will penetrate the barrier of width a and height v, which is greater than e. Now that was for a step potential. What Gamow did, the real potential as seen by the alpha particle is of this form. So what Gamow did, he said, instead of this, let us break it up into small steps. this actual potential, we are cutting it into small steps. So if the step size is very small, it's almost equal to the actual potential seen by the alpha particle. Now we have found out the transmittivity for a single step. So we have to add it up for all the steps. So if the step size is very small, we can replace the summation by an integration. So that is what Gamow did. So the total probability is a product of individual probabilities. So the exponent for the expression for transmission probability, we get a sum of the different small step potentials. By making the size of the step small enough, we can replace the sum by an integral in this range. So the expression for transmission probability can be written as e to the power minus 2 k2 dr, where dr is the width of the step, small step. Earlier, initial part of the problem, we considered it to be a for a single step. Now what we are doing, we are considering that the actual potential is a sum together of very small steps of width dr. So the transmission probability for that whole region can be represented by an integral, or we can write t is exponential minus putting down the values of v and k2. We can write it in this form. Now if v0 is the velocity of the alpha particle within the potential well, the frequency with which it will strike the wall is v0 by 2r. Let us say r is the dimension of the nucleus. So from one strike in this wall, suppose it comes and strikes it, let us say the dimension of this is r, its velocity is v. So it strikes this wall, goes back, strikes here, comes back again. So the frequency with which it will strike a particular wall will be r plus r, that becomes twice r. Time taken is between two successive strikes is 2r by v0. So the frequency is v0 by 2r times per second. So each particle has a probability t of leaking out at each strike. So the decay constant is given by the product of t and the frequency. So this is the frequency, and the transmission probability is this. So these are all mathematical steps beyond this. So what Geiger and Nuttall did, they gave a logarithmic relationship. So this is the decay constant. At each strike, there is a finite probability of the particles leaking out. So the frequency of the strikes is V0 by 2R into the transmission probability, gives us an expression for the decay constant for the nucleus. So taking the logarithm of both sides, these are mathematical steps. So VR minus E. So we get, simplifying it, we get something in this form. We take E common, so we can write it in as this. Now VR we know is equal to 2z minus 2e square by 4 pi epsilon naught r, the Coulomb potential. And VR is equal to E when r is equal to r1. At the surface of the nucleus, we said VR is equal to E at the surface of the nucleus. So at r is equal to r1, which determines the surface of the nucleus, VR is equal to E. So putting that, we get, when we put VR is equal to E at r is equal to r1, so replacing r by r1, VR is equal to E, so we get an expression for r1 in terms of E. So we can write the expression as r1 by r minus 1 half. You have to do these steps in your copy and see. So we have an integral which can be solved by the method of substitution. So what substitution we use? We use a substitution of the form r is equal to r1 cos square psi and r is equal to r1 cos square psi naught. So when r is equal to r, capital R, psi is equal to psi naught. So that is the substitution we are using. And when r is equal to r1, psi is equal to 0. If I put r is equal to r1, psi should be equal to 0, as r is equal to r1 cos square psi. If psi is equal to 0, it becomes equal to r1. So we have the above equation as, we can write it as this equation. Now R1 by R from this substitution is 1 by cos square psi. So we can write R1 by R minus of 1 as this. Also dr, if we do dr, R1 is a constant. In terms of psi, it is minus 2R1 cos psi sin psi d psi. So we can find out dr. We find out R1 by R minus 1. Putting it back in this expression, we have the equation as this. So this is R1 half. We can write it as this. Sin square psi is 1 by 2, 1 minus cos twice psi. So we have R1 here. Doing the integration, this psi, so 0 to psi naught to 0. So this is minus psi naught plus half, and integration of this is equal to this one. So we can write it as R1. We write psi naught in terms of R by R1, and psi naught, sin psi naught and cos psi naught in terms of R and R1. We get this equation. Since R is less than R1, we can write finally cos inverse. We can expand this as half pi, keeping the first two terms, and 1 minus R by R1. 1 minus R by R to the power half is almost equal to 1. So putting it back in the expression, we can write it as pi by 2 R by R1 to the power half. So putting back the values of R and R1 in terms of the atomic number, what we are doing here is basically we are putting R in terms of when R is equal to R1, E is equal to V. Using that, we are putting the value of R1 in terms of the atomic number. So this comes as this, and we are writing in terms of E, the energy of the alpha particle. So finally, we get an expression of this form. So you have to do these steps, check out the steps. So we'll end up with this expression which relates the disintegration constant with the energy of the alpha particle. So let's not confuse with this R. This R is the range of the, or the dimension of the nucleus. This is not the range of the alpha particle, this is the dimension of the nucleus. So what this relation gives us is a relationship between the disintegration constant and the energy of the alpha particle. So finally, if we put down the values of the different parameters, epsilon naught, pi, and m is the mass of the nucleon, putting down the values of the different parameters, and h cross is the Planck's constant by twice pi, putting the values of the different parameters, we'll end up with this expression. So this is the theoretical expression relating the disintegration constant of an alpha emitter to the energy of the alpha particle. So what Gamow did, he developed a theory which relates the disintegration constant of the alpha emitter with the energy of the alpha particles being emitted. And Geiger and Nuttall gave the empirical law relating the disintegration constant with the energy of the alpha particles. So Gamows theory, it tallied very well with the empirical law given by Geiger and Nuttall. So this is all about Gamows theory of alpha decay.